This is a 4/4 musical measure. 4/4 time, also called common time, means the measure can fit 1 whole note, 2 half notes, 4 quarter notes, 8 eighth notes, etc. And each of those notes has a pitch. Let's say each note can have one of 7 unique pitches, since that's how many are in a major scale. Or a minor scale. Of course, most songs use more than 7 pitches, but we'll stick with 7 for now. At the end of the video, I'll show you an easy way you can do this calculation with any parameters your heart desires. You came here to find out how many unique songs can be written in a 4/4 measure. So let's start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Stop. This seems like a waste of time. We're never going to get through all the combinations at this pace. The problem we're trying to solve looks hard, and we need to know where to start. Counting possibilities like this is a good way to test the waters and make some observations. That's how I originally started tackling this problem, and here's one observation we'll make right away. If a whole note can be split into half notes, and half notes can be split into quarter notes, then where does the splitting stop? There's no rule in music theory saying the notes can't be infinitely small, so you could have an infinite number of musical compositions just by subdividing the notes forever. I'm not really happy with that answer, especially since most songs don't use anything smaller than, like, 16th notes. A composition like this would be unconventional, to say the least. So let's set another limitation and say that our notes can't be any smaller than 16ths. Again, any parameters your heart desires at the end of the video. Let's keep counting. 11, 12, 13, 14, 15, 16, 17, 18. Okay, new observation. This half note has 7 possible pitches, but for each of those 7 possibilities, this half note has 7 possibilities. So let's skip the counting altogether and call this 7 times 7, 49 arrangements of 2 half notes. Now that that's done, let's look at smaller notes. We could split both of these half notes into quarter notes, or we could just split the left half note into quarter notes, or we could just split the right one. And these would all count as unique rhythms that we need to account for. And that'll get even harder to keep track of when we split the quarter notes into eighth notes, and the eighth notes into 16th notes. Yikes. Let's try something different. Instead of starting with a whole note and dividing, let's start with 16 16th notes and try grouping them. For example, if we group them like this, they become 4 quarter notes. Like this, and they become 1 quarter note, 2 eighth notes, 1 16th note, 1 dotted eighth note, and then 1 more quarter note at the end. Now we've got a much easier problem. If we just figure out how many ways these 16 16th notes can be grouped, that will tell us how many rhythms are possible. But that doesn't take rests into account. Where did you come from? Rests. You know, the silences in between notes. Oh yeah, so just like regular notes, rests can have any arbitrary duration, really. You can have half rests, quarter rests, eighth rests. So actually we can just work with the regular notes and say that each of them can have one of 2 possible states. Either it's a note or a rest, either it's a sound or a silence. In fact, we could just say that each note has a total of 8 possible variations. It could be one of the 7 pitches on our scale, or it could be a rest. So we'll come back to this. First, we need to focus on rhythm. How many ways can these 16 16th notes be grouped? Well, let me ask you this. How many ways can 16 be written as a sum of other numbers? Those are called compositions. Welcome to combinatorics, and asking how many compositions of 16 there are is the same as asking how many ways 16 16th notes can be grouped. As luck would have it, our good friend Wikipedia provides an easy way to calculate how many compositions of 16 there are. This method works for any number, so let's start with an easier example. Compositions of 4. We write 4 ones in a row, separated by boxes. There are 3 boxes, one less than the number of ones, and each box can either have a plus or a comma in it. If I fill the boxes like so, it becomes 1 plus 1, 1 plus 1. That simplifies to 2, 2, and there we have one possible composition of 4. If we fill the boxes differently, it produces a different composition. Every time. In this case, we find there are 8 compositions total, but to figure out the number of compositions without having to list them all by hand, we'll use the following formula. We'll go 2 possible states for the first box, times 2 possible states for the second, times 2 states for the third. That's 2 to the power of 3, or 8 compositions. So the solution is just 2 to the power of however many boxes we have, which is always one less than the number of ones. Therefore, the formula for the number of compositions for any number n is 2 to the power of n minus 1. To calculate how many compositions of 16 there are, all we gotta do is input 16 in the formula. 2 to the power of 16 minus 1 is... Wow, I'm glad we didn't try counting by hand. So there's our clear answer for how many rhythms are possible, but how does pitch tie into that? Remember, we've accounted for all possible durations of notes, but each note still has 8 pitch variations, 7 possible pitches, or a rest. This is where I got a bit stumped. We know how to calculate the number of rhythm possibilities and the number of pitch possibilities. Now we need to figure out how to put the two together to calculate the total number of overall possibilities. If we know how many notes are in the measure, say 4 for example, then to get the number of pitch possibilities, we can multiply 8 by itself that many times. 4 notes means 8 times 8 times 8 times 8, or 8 to the power of 4 pitch possibilities. Let's imagine that we somehow figured out that there were, say, 100 rhythm possibilities that have exactly 4 notes. Then we'd just multiply the number of pitch possibilities by the number of rhythm possibilities to get the total number of possible measures that have exactly 4 notes. If we could repeat this for measures that have exactly 1 note, exactly 2 notes, exactly 3 notes, 5 notes, 6 notes, all the way to 16 notes, and we added all those possibilities together, then we would have our grand total. So the last step in solving this puzzle is to figure out how to calculate the number of rhythm possibilities that have a specific number of notes. Let's go back to compositions. Here we have our 16 16th notes from before. Let's start by saying we want to figure out the total number of rhythm possibilities that have exactly 4 notes. That means these 16 16th notes will be grouped into exactly 4 groups. This is analogous to asking how many ways can you write 16 as a sum of exactly 4 numbers. If we break it down again, we've got 16 ones, each separated by a box, and like before, each box can either have a plus or a comma in it. But this time there's a small difference. Let's ignore the pluses for a moment because the commas are what's important here. The commas separate the groups, and since we want exactly 4 groups, we can conclude that those 4 groups must be separated by exactly 3 commas. So if we're looking at these boxes, exactly 3 of them will have commas, and the rest will have pluses. There are a lot of boxes for those 3 commas to choose from, and if we figure out exactly how many arrangements those 3 commas can have, that will tell us how many possible rhythms have exactly 4 notes. At this point, I got stuck again. How do we calculate the number of unique positions these 3 commas can have? I tried researching this to no avail, and let me tell you right now, if you think we can solve this using factorials, let me respectfully prove you wrong. In short, this and this should not count as separate possibilities, but they will if you calculate using factorials. So I once again had to resort to playing around. I'll start by putting all 3 commas in the 3 leftmost positions. From now on, I'm going to call them positions rather than boxes. So that's 1 possibility counted so far. Now I'll take this comma right here and move it 1 spot over. Boop. That's 2 possibilities counted. And 3 possibilities. 4 possibilities. Okay, let's pick up the pace. Once I'm down to here, I've exhausted all 13 positions of this rightmost comma. So now I'll take this bad boy and move him over 1 spot. I'll bring this comma back over to the left and repeat the process. This time I count 12 positions, which I'll add to the 13 from before, but let's keep going. I move this bad boy over another spot and repeat again. This time I count 11. I'm sure you're starting to see the pattern. We go again, and again, and again, until finally both commas are all the way over to the right. And just look at this sum. 13 plus 12 plus 11 plus 10 plus 9, all the way down to 1. That's pretty interesting. That adds up to 91, and we call this type of number a triangle number. Here's why. 13 dots plus 12 plus 11 plus 10, boom, you've got a triangle. 91 is called the 13th triangle number because the sum starts with a 13. This will become important in a minute. So we've exhausted all possible positions for these 2 commas. You may see where I'm going with this. Now we take this guy over here who's been patiently waiting, move him over 1 spot, and the entire process resets. So let's see how this plays out. Okay. I see 12 plus 11 plus 10, yada yada yada, and this time the sum we got is 78, the 12th triangle number. Interesting, interesting. Now this comma moves over 1 spot again, and let's play it out one more time. and we got the 11th triangle number. Okay, look at that. So you see how this is going to play out. When we work out all the possibilities by hand, the total sum is the 13th triangle number plus the 12th triangle number plus the 11th plus the 10th all the way down to the first triangle number. That's amazing. You may be wondering, does this type of sum have a name as well? And it does. Do you want to guess what it's called? You're wrong. It's called a tetrahedral number. Why is it called that? Well, let's take our 13th triangle number and let's add the 12th triangle number on top. Then let's stack on the 11th and boom, 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 bam, you've got yourself a tetrahedron, a bunch of triangles stacked together into a three-dimensional shape. Mind-blowingly, the 13th tetrahedral number is equal to the number of rhythms possible with exactly 4 notes. And in case you're wondering if there's a name for sums of tetrahedral numbers, you're right, there is. We get into those when we have 4 commas in our set instead of 3. They're called pentatope numbers. A pentatope is a bunch of tetrahedrons stacked on top of each other in the 4th dimension. I know. I have too much free time. But seriously, math in higher dimensions is a real thing, and you can learn much more about it in Matt Parker's Things to Make and Do in the 4th Dimension. Highly recommend. And yes, there are numbers past pentatope numbers, but at that point they stopped giving them special names. You can learn more about these types of numbers in an article I've linked in the description. Okay, it's been, I don't know how many minutes it's been, but we still don't have an answer to this video's question. So let's fix that. The number of rhythm possibilities, which contain 4 notes, was the 13th tetrahedral number, but we want to do this same calculation for all numbers of notes from 1 to 16. Here's how we do that. This is a formula that I devised, but I don't want to bore you with how we get this formula. It's not hard to figure out, so let's just jump to what the values are. Sure enough, when we add all these values together, we get 32,768 rhythm possibilities, the same number we calculated before. So that's a pretty foolproof guarantee that our math is correct. However, now we can go row by row, multiplying the number of rhythm possibilities by the number of pitch possibilities for each row, and then adding up the grand total for our final answer. Here it comes, the moment you've all been waiting for. Ladies and gentlemen, the number of unique musical compositions you can fit in one 4/4 measure is 1,647,129,056,757,192. So yes, humanity is a long way from running out of new music. In fact, to calculate the number of possibilities for 2 measures, you would simply multiply this number by itself. For each additional measure you add, the number of possibilities grows 1 quadrillion times larger. That's incredible. But wait, that's only the calculation when you work with those arbitrary parameters we set. What if you want your composition to include more than 7 notes, or have notes smaller than 16th notes? Introducing my grand invention, the Measure Possibilities Calculator. Input your scale, input the smallest note allowed, you can even change the time signature, and all of these can have custom values, so go crazy. Your answer appears in the blink of an eye. You want triplets? A triplet is 1/3 of a quarter note. 1/3 of a quarter note is 1/12, so set your custom smallest note allowed to a 12th note. That's not even a thing in music theory, but it works. But wait, I hear you cry, how do we know this calculator is legit? Simply set your scale to major, select the 16th note as the smallest note allowed, set the measure to 4/4, and boom. Same answer as we got in this video, 1.6 quadrillion. And as further evidence, set the smallest note allowed to a whole note. Total possibilities, only 8, because that whole note can't be divided at all. It can only be a whole note, and a whole note can only be one of the 7 pitches on our scale, or a rest. QED, calculator is legit. But wait, using your method, this measure and this measure would count as different compositions, even though both are total silence. You're right. You are. My method isn't perfect. These 2 musical compositions are counted separately by my method, and they do sound exactly the same. But they are at least written differently. And let me reassure you that even if we don't factor rests into our calculation at all, the number of possibilities is still a very impressive 200 trillion. So anyway, between doing this calculation, learning about combinatorics and tetrahedral numbers, and designing and programming an online calculator, I think I've had my fun. So thank you for joining me as I recount this mathematical adventure. I'm gonna go, recharge. One quadrillion, 100 and... 1 quadrillion 129 billion 5. Oh, dang it.